All right, welcome to the deep dive. Today we're pulling from your sources to unpack a system you definitely see everywhere online, but maybe don't stop to think about the URL shortener.
Yeah, exactly. Those tiny links, like bit.ly something that somehow get you to a much longer web page.
It seems so simple on the surface.
It does. But actually designing one that can, handle the massive scale of the internet, that turns out to be a really classic system design challenge.
Okay.
And it's a fantastic way, I think, for anyone listening to sort of dive into this kind of thinking. It shows how these core principles apply even to tools that seem pretty straightforward.
So our mission for this deep dive is basically to understand the core requirements, figure out the key pieces you need architecturally, and then really explore the interesting challenges. Things like making it fast, keeping it reliable, and handling, well, literally billions of links and millions of users daily.
Yeah, the scale is pretty mind-boggling when you dig in. Let's get started.
Okay, so let's start right at the beginning. Why? Why do people even bother using shortened URLs in the first place?
Well, the material lays out some really practical advantages. I mean, for users, it's often just convenience, right? And readability.
Easier to share, maybe.
Definitely. A short link looks cleaner. It's way less prone to typing errors if you are typing it. And it's crucial when character counts matter. Think text messages or, old school Twitter.
Ah, right. Character limits. Makes sense.
And even from a data standpoint, they technically take up less storage space, though that's probably a minor point for most users.
Okay, totally get the convenience factor. Nobody wants to type out a 5-line URL they saw on a poster. But your sources also mention some downsides, specifically if you rely on someone else's shortening service.
That's a really important point. You do lose some brand control. The link becomes, say, bit.hal your thing instead of your-cool-brand.com.
Right. You're promoting their brand, too.
Exactly. And then there's the risk factor. What if that third-party service shuts down? Or gets acquired and changes things? All your links could suddenly break.
Oof. Yeah, that's not good.
It requires a level of trust. Plus, getting those really catchy custom short names on the big public services, that can be pretty competitive. So these are all reasons why some companies decide, okay, we need to build our own.
Gives them control.
Total control over the service, the branding, the data, the lifespan of the links.
So, okay, let's imagine we are building our own. What are the absolute must-have features? The core functionality?
At its heart, it's pretty simple functionally. You need to be able to take a long URL as input, and your system has to generate a unique shortcode for it, giving you back the short URL.
Input long, get short.
Precisely. And the flip side. Someone gives your system the short URL, maybe by clicking it, and your system must redirect them reliably to the original long URL.
Input short, go long. That's the core loop.
That's the absolute essence. Now, the sources do mention common optional things you might add, like letting users pick their own custom short link, sometimes called an alias.
Like your shortener.com campaign.
Exactly. And maybe setting an expiration date, so links don't just hang around forever if they're for, say, a short-term promotion.
What's usually not included, at least initially?
Things like full user accounts, login systems, detailed analytics on who clicked what, when those are often considered out of scope for the basic version. Although, interestingly, the way you handle redirects can enable analytics later. We'll probably get to that.
Okay, redirects. That touches on performance. Let's talk about the non-functional requirements. How well does this thing need to work?
Oh, exceptionally well. This is where it gets challenging. First off, those shortcodes must be unique. Absolutely critical. No two different long URLs should ever end up with the same shortcode.
Makes sense. Collision would be bad.
Very bad. Then, redirection speed. It needs to be incredibly fast. The sources mentioned aiming for under 100 milliseconds. Users expect basically instant.
Wow. Okay. Less than 1/10 of a second.
Yep. And the system itself needs to be highly available, like always on, aiming for 99.99% uptime as mentioned, which is pretty standard for critical web services.
4 nines. Okay.
And then there's the scale. It has to be able to handle potentially, 1 billion or more stored URLs over its lifetime and process maybe hundreds of millions of redirection requests every single day.
1 billion URLs.
Yeah.
That really frames the challenge differently.
It really does. And the sources add a couple more points.
Mm-hmm.
The short links themselves should ideally be somewhat readable and typable.
So not just random gibberish.
Right, which influences the characters you choose to use in the shortcode. And related to that, they also need to be unpredictable for security reasons. You shouldn't be able to just easily guess the next valid shortcode someone created.
Okay, so unique, fast, Highly available, massive scale, readable, and unpredictable. That's quite a list.
It is.
What's the single most important factor or usage pattern from the sources that really shapes how you design this?
I'd say it's the read-to-write ratio. This comes up again and again. People click on existing short links. That's a read operation. Vastly, vastly more often than they create new short links. A write operation.
How much more?
The sources suggest figures like maybe 1,000 reads for every one write, sometimes even higher ratios.
Wow, 1,000 to 1.
Yeah. And this imbalance is absolutely key. It means your system's architecture has to be overwhelmingly optimized for handling a huge volume of read requests extremely quickly. Writes are less frequent, but they still need to be correct and reliable.
So that read-heavy nature basically dictates the design choices.
Pretty much. It influences everything from caching strategies to database selection.
Okay, that makes sense. So let's start putting the pieces together. What are the basic components or entities involved?
At a very high level, you need some way to store the mapping, right?
Yeah.
The link between the short code and the original long URL.
Yeah.
So conceptually, your main things are the original URL itself, the generated short URL or code, and maybe you think about a user. Even if you don't have logins initially, you might store which user created a link, perhaps.
And how do people or maybe other computer systems interact with this? Through an API, I assume.
Exactly. You typically define an API. You'll definitely need an endpoint to create a new short URL. That would likely be an HTTP POST request.
What goes in the POST?
You'd send a long URL you want to shorten, and maybe those optional things like a desired custom alias or expiration time. The API endpoint receives this, does the work, and then returns the generated short URL. That POC request is what triggers adding a new mapping to your database.
Okay, that's creation. What about using the link, the redirection?
That's usually handled by a simple HTTP GET request. When someone clicks short.liabc123, their browser sends a JT request to your server asking for the resource ABC123.
And the server just looks that ABC123 up.
Precisely. It extracts that short code, looks it up to find the corresponding long URL, and then tells the browser where to go. The forces also mention you might eventually add other API calls, maybe for deleting or updating links, but create and redirect are the core.
Got it. Let's walk through an example. Say I want to shorten a really long URL, like myfavoritewebsite.com, deep dive article about something.param1 am param2b. What happens step by step when I hit your create API?
Okay, so you send that long URL in your POST request. One of your server instances receives it. First, I might do a little validation, like, is this a valid URL format? Does it start with HTTP or HTTPS? Things like that.
Basic checks.
Right. Then, the crucial step, the system generates a unique shortcode for it. We'll have to dig into how it does that later.
Okay, magic happens.
Magic happens, a shortcode pops out. If you happen to suggest a custom alias, like cool stuff, the system would check if cool stuff is already taken. If not, it uses that. Otherwise, it generates one.
Makes sense.
Then it stores the mapping. This shortcode links to that long URL, maybe with an expiration date, into your chosen database.
Persists the data.
Exactly. And finally, the server sends a response back to you, usually containing the full short URL, like your shortener.com, FK size, ASA789.
Okay, creation seems fairly logical. Now, the other side. Someone, maybe me, clicks on yourshortener.com/YZ789. What's the flow for the redirect?
All right, so your browser sees that URL and sends a GT request to the yourshortener.com server asking specifically for the path YZ789.
The server gets the request.
Yeah, the server receives GET lies YZ789. It immediately looks at that path, extracts the shortcodes YZ789, and queries its data store, probably checking a cache first. Then the database asking, what long URL corresponds to YZ789?
Finds the long URL we stored earlier.
Hopefully.
Oh.
Assuming it finds it and the link hasn't expired, it retrieves that original long URL, myfavoritewebsite.com/deep dive, and so on.
And then?
Then, the server doesn't actually send the content of that page back. Instead, it sends a special HTTP response back to your browser. This response has a status code indicating a redirect, like 301 or 302, and includes a location header containing the original long URL.
So it tells the browser, nope, don't look here, go there instead.
Exactly. It's an instruction. And the browser automatically follows that instruction, making a new request directly to the long URL. Usually this happens so fast, the user barely notices the intermediate step.
You mentioned 301 and 302 redirects. The sources discussed why one is usually preferred.
Yeah, this is an important detail. A 301 redirect means moved permanently. A 302 redirect means found or moved temporarily.
What's the practical difference for the user or the shortener?
The 301 tells the browser, this move is permanent, you can remember this. So browsers often cache 301 redirects very aggressively. If you click the same short link again later, your browser might just remember the final destination and go straight there, without even contacting the shortener service again.
Ah, so the shortener loses visibility on future clicks.
Exactly. And you lose control. If you later wanted to change where that short link points or delete it, cached 301s in users' browsers wouldn't know. A 302, being temporary, tells the browser, go here for now, but check back with me next time.
So browsers usually don't cache 302s.
Typically not, or not as aggressively. This means every click on a short link using a 302 redirect does come back to your shortener server first.
Which seems better for the service, right?
Generally, yes. The sources argue 302 is preferred for URL shorteners because it gives the service ongoing control. You can update the destination, track clicks accurately because every click hits your server, maybe implement logic based on the clicker's location or device type.
Oh, okay. That allows for analytics too, like you hinted earlier.
Precisely. Since every click comes through you, you can count them, log information, etc., which is much harder if browsers are caching 301s and bypassing you.
All right, that clarifies the basic creation and redirection flows and the redirect type choice. Now let's really dig into the deep design challenges. First up, generating those unique shortcodes. How do you do that efficiently, reliably, and make them unpredictable at massive scale?
Yeah, this is probably the most interesting algorithmic part. You need codes that are short, unique, efficient to generate, and as you said, hard to guess.
Seems like a tall order.
It is. A common approach discussed in the sources starts with getting a unique numerical ID for each new URL. Think of it like an auto-incrementing primary key in a database, but one that needs to work across potentially many servers.
Like a really big counter?
Sort of, maybe a 64-bit integer. This guarantees uniqueness. But a huge number like, 5 trillion isn't very short if you just write it out.
Right, that's not a short URL.
Exactly. So the trick is to encode that large unique number into a shorter string using a different base system.
Like converting decimal to hexadecimal.
Precisely like that, but going further. Instead of base 10, digit 09, or base 16, 09 plus AF, you use a larger set of characters. Base 62 is common.
Base 62, what characters are those?
That uses all 10 digits, 09, all 26 lowercase letters, AZ, and all 26 uppercase letters, AZ. That gives you 62 possible digits for each position in your string.
Ah, so you can represent a much bigger number in fewer characters.
Exactly. A 64-bit number, which is enormous, can be encoded into a base 62 string that's maybe only 10 or 11 characters long, which is much more manageable for a short URL.
Okay, but the sources specifically highlighted base 58. Why drop 4 characters from base 62?
That's purely for human readability and avoiding mistakes. Base 58 takes base 62 and deliberately removes characters that look confusingly similar. Like the digit 0 and the uppercase letter O, or the uppercase I and the lowercase l. They look almost identical in many fonts. Base 58 removes those. It also removes the plus and symbols, which sometimes appear in other base encodings like base 64, because those characters can cause problems when used directly in URLs.
Ah, clever. So base 58 makes the codes easier for people to read and type correctly if they ever need to.
That's the idea. It makes them more robust for sharing visually or verbally.
Okay, so the unique number gives uniqueness. The base conversion, like base 58, gives shortness and readability. What about unpredictability? If you're just encoding sequential IDs, say 1, 2, 3, wouldn't the encoded strings also follow a predictable pattern?
You're absolutely right. If you encode ID 1000, then ID 1001, the resulting base 58 strings might look related. Or at least you could potentially guess near neighbors. That's not ideal for security.
So how do you make them unpredictable?
The sources suggest a neat trick. Don't just take the next sequential ID. Instead, you could, for example, pre-generate a large pool of unique 64-bit IDs within a certain range. Think of it like having a big bag of unique lottery numbers.
Okay.
When you need to create a new short link, instead of taking the next number off a counter, you reach into the bag and pull out a random ID from the pre-generated pool. You then encode that random ID into base 58.
Ah, so the relationship between sequentially created links is broken because you're using randomly selected IDs.
Precisely. You mark that ID as used so you don't pick it again, but the resulting shortcodes have no obvious sequential relationship, making them much harder to guess.
That's a really elegant solution. Okay, so we have a way to get unique, short, readable, and unpredictable codes. Now let's switch back to the other core function. Redirection, making it fast under that 100 meters target. Where's the biggest slowdown likely to be?
It's almost always the database lookup, or more generally, the data store lookup. When a request for GuysYZ789 comes in, you have to find the long URL associated with GuysYZ789 if your database has billions of entries.
Searching that every time is going to be slow.
Potentially very slow, especially under heavy load. You absolutely cannot afford a full table scan or even a slow index lookup for every single redirect.
This feels like a classic caching problem.
Textbook case. Caching is absolutely non-negotiable for making redirection fast at scale. You need a caching layer sitting in front of your main database.
What kind of cache?
The sources mention things like memcached or Redis. These are in-memory data stores, optimized for extremely fast key value lookups. The key would be the short code, SYZ789, and the value would be the long URL.
So how does that fit into the redirect flow?
Okay, request for SYZ789 comes in. Step 1. Check the cache. Do I have SYZ789 in memory? If yes, a cache hit, you grab the long URL directly from the cache, which is incredibly fast, likely sub-millisecond. You then send the redirect response.
And if it's not in the cache miss.
If it's a cache miss, then you go talk to the main database. You do the potentially slower lookup there to find the long URL for SYZ789. Once you get it from the database.
You send the redirect.
Right, you send the redirect response to the user, but you also immediately store that SYZ789 long URL mapping into the cache.
So the next person who clicks that same link gets a cache hit.
Exactly. Popular links quickly end up in the cache and are served extremely fast, taking a huge load off your main database. This strategy is crucial for handling that 1,000 to 1 read-write ratio.
Makes total sense. Now, the sources also mentioned something potentially even faster, using CDNs or edge computing. How does that work?
Right. This is taking caching sort of to the next level geographically. Yeah. A CDN, or content delivery network, has servers distributed all around the world, physically closer to your users.
Like Akamai or Cloudflare.
Exactly. Edge computing means you can actually run some of your application's logic on these CDN edge servers, not just cache static files.
So you could run the redirect logic itself out on the edge?
Potentially, yes.
Yeah.
You could push the short code to long URL mappings, at least for popular links, out to these edge servers. When a user in, say, London clicks a link, the request might hit a CDN edge server in London.
And that edge server already knows the mapping?
If it's cached there, yes. The edge server itself can perform the lookup and issue the HTTP 302 redirect directly back to the user's browser, maybe without ever having to contact your main origin servers or database back in, say, Virginia.
Wow, that would cut latency dramatically.
It really can, because you're minimizing the physical distance the network traffic has to travel. It's a powerful technique for global high-performance services.
What are the downsides? Sounds complex.
It definitely adds complexity and cost. You have to manage distributing the data and logic to the edge, and ensuring consistency becomes harder if you update or delete a link. How do you make sure all those edge caches around the world get invalidated quickly? But for shaving off those extra milliseconds, especially for a global user base, it's a significant optimization.
Okay, so unique codes handled, fast redirects via caching, and maybe CDNs. Now, the big one. Scaling to handle billions of URLs and millions, maybe hundreds of millions of daily users. Let's talk about the data first. How much storage are we actually talking about?
Let's use the numbers mentioned in the sources as an estimate. Say 200 million new URLs shortened per month. And maybe you keep them for 5 years.
Okay, 200 million times 12 months times 5 years. That's 12 billion URLs.
Roughly, yeah. A very large number. Now, how much space does each mapping take? You need the short code, the long URL, maybe a creation date, expiry date, user ID. Let's estimate maybe 500 bytes per entry on average.
Okay, 12 billion entries times 500 bytes. And carry the one, that's about 6 terabytes.
Exactly. Around 6 terabytes of primary data storage.
Is 6 TB a lot for a database these days?
It's significant, but definitely manageable with modern database technology. The more important point, going back to the read-write ratio, is that the database isn't necessarily getting hammered with constant writes or complex queries if the cache is effective. Writes might only be a few per second globally, based on maybe 100,000 new URLs per day. Reads are mostly served by the cache.
So the choice of database might be less critical than how you use it with caching.
To some extent, yes. The sources suggest that many different databases could potentially work traditional relational databases like PostgreSQL or MySQL or various NoSQL options.
But your materials seem to lean towards NoSQL, specifically mentioning MongoDB. Why might that be a good fit here?
The argument often made for NoSQL in cases like this centers on flexibility and scalability, especially for read-heavy workloads. MongoDB, with its document model, can be quite flexible. More importantly, its common setup uses leader-follower replication.
How does that help?
You write to the leader node, and the changes replicate to multiple follower nodes. You can then direct all or most of your read traffic the cache misses that need to hit the DB, to these follower replicas. This effectively scales out your read capacity significantly.
So you can handle more database reads by adding more replicas.
Exactly. Now, the sources contrast this with other NoSQL types, like maybe Cassandra or React, which often use leaderless architectures. Those might offer slightly higher write availability. But for this specific URL shortener problem where reads dominate, MongoDB's strong read scaling via replicas is often seen as a very good match. The potential downsides in write consistency or availability compared to leaderless systems are often considered negligible given the low write frequency here.
Okay, that makes sense, optimizing the database choice for the dominant workload, which is reads escaping the cache. What about just keeping the database online? High availability was a requirement. What if a database server crashes?
Standard best practices are crucial here. Database replication, which we just mentioned for scaling reads, is also key for availability. If the leader node fails, one of the followers can be promoted to become the new leader, usually quite quickly.
So you have redundancy built in?
Yes. And layered on top of that, you absolutely need robust database backups. Regularly taking snapshots of your database and storing them securely somewhere else. The sources mentioned using a service like Amazon S3 is critical. If something catastrophic happens, you can restore your data from a recent backup.
Okay, replication for failover, backups for disaster recovery. Got it. So we've scaled storage and reads. What about scaling the servers that actually handle the incoming HTTP requests, especially the write requests for creating new links?
This is where separating concerns helps. A common pattern is a microservice architecture. You'd likely have a distinct service, maybe called the read service or redirect service, whose only job is to handle the incoming GDT requests, check the cache, and issue redirects. It needs to be super fast and handle huge volume.
And a separate service for writes.
Exactly. A write service or creation service handles the POST requests for creating new short links. This service deals with generating the unique ID, encoding it, and writing the mapping to the database. Because the write volume is much lower, this service might need fewer resources than the read service.
And splitting them lets you scale them independently.
Precisely. If your redirects suddenly spike, you can just add more instances of the read service without touching the write service, and vice versa.
How do you distribute traffic to these multiple instances?
You put them behind a load balancer. When a request comes in, the load balancer decides which specific server instance running the read or write service should handle it. It could be random, round robin, or based on current server load. For a global service, you'd likely use a global server load balancer, or GSLB.
What does the GSLB do?
It's like a smart DNS service that directs users to the entire data center or cluster of servers that's geographically closest to them, reducing latency. Then, within that data center, another load balancer distributes requests to the individual server instances.
Okay, distributed services behind load balancers. Now let's connect back to something we talked about earlier, that unique ID generation. If you have multiple instances of the write service running on different machines, maybe even in different data centers, how do they all coordinate to get the next unique ID without accidentally generating the same one? That sounds really hard.
Yes. This is a classic distributed systems problem. Managing shared, mutable state, in this case, a global counter. You can't just have each server keep its own counter.
They'd collide immediately.
Right. So the sources suggest a common solution is to use a centralized but very fast service just for issuing these unique IDs.
Like what?
A dedicated instance of an in-memory store like Redis is often used. Redis is single-threaded, which means it can handle operations like incrementing a counter, atomically guaranteeing that even if multiple write service instances ask for the next ID at the exact same microsecond, Redis will process those requests one by one and hand out unique sequential numbers.
So every write service instance, whenever it needs a new ID, quickly asks a central Redis counter.
That's the basic idea. Since Redis is extremely fast in memory, the network round trip to ask for an ID is usually very quick and acceptable for the relatively low frequency of write operations.
But still, for every single new link created, a server has to talk across the network to Redis. Couldn't that become a bottleneck itself if writes did spike?
It's a valid concern, and the sources mention an optimization for this, often called counter batching or ID batching.
Batching. How does that work?
Instead of a write service instance asking Redis for just one ID, it asks for a block of IDs. It might say, hey Redis, give me the next 1,000 available IDs.
And Redis just increments its main counter by 1,000.
Exactly. Redis increments its global counter by 1,000 and tells the requesting server, okay, you can use IDs from, say, 5 million to 5,999.
And then that write service instance can satisfy the next 1,000 incoming create requests using IDs from its local batch without talking to Redis again.
Precisely. It dramatically reduces the number of network calls to the central counter, improving performance and reducing load on Redis, while still guaranteeing that the blocks of IDs handed out are globally unique.
It's very clever optimization. Okay, let's try to quickly pull together some of the other specific design considerations or techniques the sources mention for achieving those non-functional goals.
Yeah. So for availability, we touched on GSLBs for traffic routing, database replication, and backups, maybe to S3. Another tool mentioned is rate limiting.
To prevent abuse.
Yeah, to stop a single user or bot from overwhelming your system with too many requests in a short period. Algorithms like the fixed window counter were mentioned as a way to implement this.
Okay. And for scalability.
We talk about horizontal scaling of services behind load balancers, using microservices, and read replicas for databases. The sources also mention horizontal database sharding.
Sharding, what's that?
That's where you actually split your database data across multiple independent database servers. So maybe URLs starting AM go to server 1 and NZ go to server 2. Consistent hashing is often mentioned as a technique to decide which shard data belongs to, especially as you add more shards.
So you partition the data itself.
Right. We also mentioned distributed ID generators like Twitter's Snowflake as an alternative or complement to centralized counters, and considering databases optimized for writes, like DynamoDB, Cassandra, Bigtable, if write load becomes a problem. Plus things we already covered like rate limiting quotas, pre-generating ID pools, and load balancers.
What about readability again?
That was mainly addressed by using base 58 encoding, which removes those visually confusing characters.
Latency.
The encoding itself is very fast. The main latency concern is the redirection lookup, which is tackled aggressively by caching, potentially CDN's edge compute, and choosing databases with good read performance like MongoDB with replicas.
And unpredictability.
That key technique was randomly assigning IDs from a pre-generated pool rather than using strictly sequential ones.
Got it. Okay, the last scenario the sources brought up. What if you get a sudden massive spike in write traffic? Not clicks, but people trying to create millions of new short links all at once, maybe due to some event or bot attack, and it starts overwhelming your database write capacity.
Yeah, handling unexpected write spikes is important. The sources suggest a few tiers of solutions, short-term, quick fixes.
What could you do immediately?
You could potentially cache recently created mappings for a short time, so if the same long URL is submitted many times quickly, only the first one hits the database. You could also introduce an asynchronous processing queue.
Like Kafka or RabbitMQ.
Exactly. Your API endpoint just accepts the request very quickly, puts the create link job onto a message queue, and returns success. Worker processes then pull jobs off the queue and write to the database at a more controlled pace. This absorbs the spike.
Decouples the API from the database, right?
Right. And you might also be able to temporarily scale up your database's write capacity depending on the platform.
And for longer term, more robust solutions to handle potentially frequent or larger write spikes.
That usually involves more fundamental architectural changes. Database sharding, which we mentioned, directly distributes the write load. Using a truly distributed ID generator like Snowflake avoids the potential bottleneck of a single counter service. Maybe migrating to a database specifically designed for high write throughput, like Cassandra or DynamoDB, could be necessary.
And tightening controls.
Definitely. Implementing stricter rate limiting and quotas specifically on the creation API becomes more critical. Ensuring you have sufficient write service instances and efficient ID batching or pooling helps absorb bursts. Basically, strengthening all the components involved in the write path.
Wow. Okay. So something that seems, almost trivial on the surface, just making a web link shorter, actually forces you to think about pretty much every major challenge in designing large-scale distributed systems.
It really does. Caching strategies, database selection for specific read-write patterns, ensuring data consistency, handling distributed state like unique ID generation, achieving high availability, scaling horizontally. It's all in there.
It's a fantastic example of how understanding the core requirements and crucially the expected usage patterns, like that huge read versus write difference, completely drives the architecture.
Absolutely. That imbalance informs almost every major decision, and the specific challenges like needing short and unpredictable and readable codes lead to specific technical solutions like base 58 encoding and randomized ID assignment from pools.
It really demonstrates the trade-offs involved here.
Exactly. You're constantly balancing things.
Yeah.
Performance versus cost, like using CDNs, availability versus consistency, maybe in database choices, simplicity versus feature richness.
So thinking about all those trade-offs we discussed, performance, cost, availability, consistency, readability, it makes you wonder, if you, the listener, were building your own URL shortener service today, how would you prioritize those factors? What would be most important for your specific needs?
That's the core of system design, isn't it? Understanding the requirements and making informed choices based on those priorities and trade-offs. There's rarely one single right answer.
A perfect thought to end on. Thanks so much for walking us through this deep dive.
My pleasure. It was fun to unpack.